All right, so continuing to look at circuits. This one's a two-part problem, and one that I think is actually pretty useful because it gives you an idea as to what's actually going on in real life and factors that can affect things like circuits. This one says, a person notices a mild shock if the current along a path through the thumb and index finger exceeds 80 microamp. So what they're saying is basically you've got a person's hand, and if I put a wire here on my thumb and a wire here on my index finger, is that right? Yep, thumb and index finger. If I get a current that goes through my body of 80 microamp or above, I'll actually feel it as a little bit of a shock. So the current that I can actually feel it at is 80 microamp. Micro is times 10 to the negative 6. So this comes up to 8.0 times 10 to the negative 5th amp, or 80 times 10 to the negative 6th amp. In this case, that would be 80 microamp. So here we go. There's a conversion on that. Find the maximum allowable potential difference without shock across the thumb and index finger for dry skin resistance of 6.5 times 10 to the 5th. So they're saying that the resistance between my thumb and the index finger, they're saying, is about 6.5 times 10 to the 5th ohm. They're asking for the potential difference, delta V. Specifically, what they're asking for is find the maximum allowable potential difference without shock across the thumb. So basically, something just below this current. What we're looking for is going to be delta V, at which we end up with a current of about 8.0 times 10 to the negative 5th amp, 80 microamp, times a resistance, the resistance of our skin and our thumb and index finger, they estimate to be 6.5 times 10 to the positive 5 ohm. Now that's nice writing this out because times 10 to the negative 5th and times 10 to the 5th actually cancel out, and we have 8 times 6.5. You could also put them in completely into your calculator, but we end up with 8 times 6.5. Delta V comes up to 52 volts. Again, you put SI in, you will get SI out. We put in amp, not microamp. Amp is the SI unit. And we put in ohm, the SI unit. They will actually combine to give us a volt as our output in Ohm's law. All right? In this case, this is the correct answer that they're looking for. What they're actually saying is, if I have something less than 52 volts, it won't have enough current for me to actually feel the shock. When I get up to about 52 volts or above, for this resistance, I will end up with a current of about 80 microamp and I'll feel a shock. If it's less than 80 microamp, I won't really feel anything. That's basically what the problem is setting up, and that's not a bad approach. We're going to find, we may have talked about it in class or not, but there are different levels of current that can start affecting your body badly. The potential difference, the voltage, doesn't actually do that much to your body. It's the current that actually causes interactions. So for instance, the human heart, under many conditions, it varies from person to person, but the rough estimate that I always remember is about 50 milliamp is where it starts becoming very dangerous for the human heart. And so there are places where we have specific values that we know, hey, this is starting to get dangerous. We don't want to have that in a human. Now, I said this was a two-part one. They go on to then say, okay, this is all well and good, except this time you're going to get your hands wet. And this is where we incorporate some ideas with water. Water can change the conductivity if it's got, well, some of the surface properties that it does. And so it can change how electricity can get into and out of your body. Let's see what effect that has. Now this says that if I have my skin is wet, that we have a resistance of 3,000 ohms. In other words, 3 times 10 to the 3rd ohm. 3,000. And they want to know the maximum allowable potential difference without shock across the thumb, which means we're still dealing with, remember, for us as humans, at least the number that they give us, probably somewhere in this ballpark would be the real number. I don't know it right offhand. It's not one that I've actually studied, but there would be a threshold where if we have a current beneath that, our body would just kind of shrug it off and we wouldn't really feel it, and there comes a point where we would start to feel it and it would be unpleasant. They're claiming 80 microamp. We're still dealing with the same hand, and so we would end up with this. Delta V in this case is going to be equal to 8.0 times 10 to the negative fifth amp, just like we talked about before, that's 80 microamp, times our resistance of 3 times 10 to the third ohm. Here's where things get a little bit trickier. We're going to have 8 times 3, so that's 24, but the times 10 to the negative 5 and times 10 to the third don't actually cancel each other out. In this case, we would end up with times 10 to the negative 2. Basically, you can work around with some of the variables on that. If you're not as comfortable with that, please feel free to put it into your calculator. But we have a factor of 1,000 and divided by 100,000, so the thousands cancel out and we're left with divided by 100. We should end up with a delta V of, if I'm doing this correctly, it'd be 24 divided by 100, 0.24 volts. Check. That is what we have listed as the correct answer. This is important to note because there's a big difference between 52 volts and 24 volts. Or I'm sorry, 0.24 volts. There's a very big difference between those. And that's why it can be especially dangerous to be dealing with electrical objects around sources of water. They can very much change the resistances involved. That doesn't mean that water itself is a particularly good conductor or bad. There are other factors that can go into it. But this is one of the things that I do want to bring up. I haven't checked the veracity of these numbers themselves. These may be human-generated ones. I know that they randomize some of the numbers, but it is something to take into account. We can change the resistance of things by changing some of their physical properties.